That biker and I are both wearing a watch. Assuming no defects, even though one is moving, your intuition would tell you that they would tick at the same rate. But your intuition would be wrong. It turns out that time actually does depend on velocity. And this effect has huge implications for space travel. I'm Matson, and welcome to Einstein's theory of relativity and the twin paradox.
To understand the twin paradox, we must first understand this theory. Although its implications are numerous, for our purposes we will focus on just 2 points. First, all observers' viewpoints are equally valid so long as they are inertial. An observer is any object. It could be a person, a rock, or even a fantasy creature. Inertial means that the object's speed and direction of motion aren't changing. So the first point can be rewritten as, all objects' perspectives are equally valid so long as their speeds and directions of motion don't change. The perspectives of a piglin sitting in a non-moving minecart and a piglin in a moving minecart are both valid. In empty space, we can't tell which one is really moving. Inconceivable! However, a piglin in an accelerating minecart, or one that turns around, doesn't have a valid viewpoint because it can feel its velocity changing and knows that it's the moving one. This next part is tricky. When you see something move close to the speed of light, you see its flow of time slow. Einstein's theory tells us that time's flow isn't absolute. Each piglin sees the other's time slowed. Because we can't tell which is moving, both perspectives are valid. These two piglins never meet, so the perspectives can coexist. It's crazy, but this time dilation is real. Like speed, gravity also slows down time by little. GPS satellites feel less gravity than us, leading to a difference in their clocks that they must account for. In our analogy, the piglins had no conflict because their perspectives were kept separate. But what if they were to meet? Imagine that a piglin travels away close to the speed of light for a few years. The piglin left behind would see his twin's high speed and conclude that when he returns, he will be younger because his clock will be slowed. But the traveling twin sees his brother moving quickly and so thinks that he will be younger. Who is right? This is the twin paradox. The answer lies in the fact that the moving piglin must turn around. This act means that his direction of motion must change from away to towards his brother, producing an observable effect. This reveals that he is the moving one and discredits his perspective. Therefore, the traveling twin will be younger upon his return. So what does the moving twin see? For most of his trip, he sees his stationary twin with a slower time for 2 main perspectives, going away from and towards his twin. But as he turns, he goes through an infinitude of intermediate perspectives, each of which has been seeing the stationary twin a slightly different way. As the moving twin passes through all these perspectives, he sees his twin's clock speed up drastically. The math is abstract and requires use of complex tools like space-time diagrams, but it turns out this speed-up always precisely cancels out the slowing down seen before and after. This has amazing implications for space travel. If a future spaceship took 100 years to travel to the nearest star and back, we would expect most of the passengers to be dead on return. But if they travel near light speed, they might only experience a fraction of that time. Truly, Einstein's theory is amazing. It sounds insane, but somehow it manages to perfectly describe our universe. Perfectly describe our universe? You forgot about we particles. We're loyal to quantum mechanics. We declare war!